Hi everyone and welcome back! This presentation introduces you to some insight regarding the implementation of ProFAX. The first step we took has been a profiling of the application we wanted to accelerate. This procedure allowed us to find the bottleneck procedures in the program that are, in fact, the most compute-intensive function. Secondly, we used an instrument called the roofline model. This chart depicts the relation between floating point performance and the operational intensity of a given code, and it is used to predict the performance of a system given a target board. In order to exploit this graph and predict system performance, the first thing we had to do is a stated code analysis of the code we wanted to accelerate. The stated code analysis consists in counting the amount of operations performed by the kernel, that is the part of the algorithm that we want to accelerate in hardware, and dividing this number by the amount of DRAM traffic from the kernel to the memory and vice versa. The division provides a ratio called the operational intensity. Given this number, it is possible to predict system performance thanks to the roofline model. For the algorithm we are presenting here, the operational intensity is equal to 52 operations per byte, that, for our target board, results in expected performance in the order of 200 gigaflops. For what concerns the hardware implementation, we ported our kernel in order to be usable with Vivado HLS, where we exploited all the potentiality of the tool by applying pragmas and optimization at different levels. Then, we integrated our IP core into the SDXL framework that automatized the hardware design flow, reducing the errors that we could have introduced by creating the final architecture for the FPGA manually. SDXL is the new tool developed by Xilinx that offers a complete automation of all the steps of the hardware design flow. In fact, given a high-level code that could be written in C, C++, or even OpenCL, allows to optimize it and then automatically generates the bitstream for the target FPGA, as well as managing the runtime of the program. Now we will go through the problem we had in optimizing this code, as well as the optimization we introduced. The first problem we had has been that the code we wanted to accelerate was written in C++. The greatest problem in this has been that inside the algorithm, dynamic memory allocation was performed, and this procedure is not allowed in hardware. For this reason, we translated our code in OpenCL, and we knew that the SDXL framework was able to support it as an input language, but unfortunately, the version of SDXL we were using did not support some of the mathematical libraries we needed to perform the calculation yet. Hence, we had to translate our final code in pure C. Secondly, we found out that it was too expensive to read every variable from DRAM. Furthermore, in order to increase the performance of the code we were writing, we knew we had to have data locality, because only in this way it would be possible to efficiently read from DRAM. Also, the SDXL framework does not support the streaming interface yet. Hence, the only way to get better performance is by achieving the memory burst. And in order to get the memory burst, we need to read sequential cell in memory. For all this reason, we decided to move the input variables from DRAM to VRAM. And we do this by compressing the input variables in 2 big buffers and reading the whole amount of data at the beginning of the computation, and then reading it from VRAM. In this way, we can speed up the computation, as every time the data needed for the computation is locally stored. For all these reasons, we decided to move the input variables from DRAM to VRAM, and we do this by compressing the input variables in 2 big buffers and reading the whole amount of data at the beginning of the computation, and then reading it from VRAM. In this way, we can speed up the computation, as every time the data needed for the computation is locally stored. This optimization allowed us to speed up the communication over the input-output interfaces. However, it has not been enough to achieve a good increase in performance. In fact, the kernel was still slow in executing the algorithm. What we noticed is that the code we were accelerating is particularly loop intense. Hence, we try to maximize the pipelining of the loop present in the code. However, the area on the FPGA is limited and it is not possible to completely pipeline all the loops. Furthermore, Our goal has been to find the best trade-off between the amount of loop we were pipelining and how much area we were occupying. The goal of pipelining loops inside the code has been in particular of achieving an initiation interval equal to 1 for all the loops we decided to optimize. An initiation interval equal to 1 allows us to have loops that are able to produce one result each clock cycle of computation, and it is the best we could achieve from this optimization. However, the area on the FPGA was not the only problem in trying to accomplish this goal. In fact, we found out that in some of the loops there was some read after write hazard, and as this is a true dependency, it was impossible to achieve the one result produced every clock cycle. The solution we found to this problem is called reduction, and it is described as follows. Let's start from the consideration that pipelining all the loop is impossible, as too much area would be required. Considering the picture showed in the slide, the variable sum is increased multiple times, and this introduces a read after write dependency that does not allow an initiation interval equal to 1, but rewriting the code as described in the picture, we are able to store the intermediate result of the computation in a different cell of an array, so that there is no dependency and the loop can produce one result each clock cycle. Obviously, we need then multiple loops that will sum up the two sequence cells until the final result is obtained. An example of this is the last chart appeared in the lower right corner of the slide. Once all the intermediate results of the computation are stored in an array, we would need other two structures in order to sum up the values and obtain the final result. This optimization allows us to remove the dependencies between iteration of a loop when updating the same variable, as it stores each intermediate result of the computation in a different cell of an array, and creates multiple temporary buffers where the values are summed up until the final result is obtained. Among the future works, we want to increase the amount of data that is sent into the FPGA. Increasing the amount of data sent to the FPGA would result in increasing the computation on the board, that will finally result in increasing the performance of the system. Secondly, the function we are accelerating is composed of three main functions, and these functions are independent one from each other. Hence, we could achieve a further speedup by executing all these functions in parallel. And this is not all. We could in fact increase the parallelization by instantiating more than one kernel in parallel working on the same FPGA board. The different kernels would perform the same calculation for different protein structures, so that we could evaluate more than one structure at the same time. That's all for this presentation. Thanks for watching. Remember to visit ProFAX on Facebook, Twitter and SlideShare.